All right, this is the second review session. Review number 2. Dynamics, Newton's laws of motion. I do want to add a couple things, if I could, to the previous lesson, kinematics, that I did not mention that might be worth pointing out. First, let's move this. First is graphs can be pretty challenging sometimes. For example, let's just say there's two different problems that I consider challenging. A ball is launched straight up into the air and then goes up to a highest point and comes down. It doesn't really move over to the right. It just goes straight up and straight back down. And they ask, what would a position versus time graph look like? Usually it'd be y here, y versus time. I think they still put x, but position versus time graph. I'm going to stick with x. College it'll be y because that's the y-axis that goes up. What would an x versus t graph look like? I'll let you think about it for a second. For ball going just launched from the ground, just like throwing a basketball, but in my real world, you know, in my case, in the real world, if I threw something, it would start at some initial height, I don't know, like 5 feet or something. Assuming that just launched from ground level, straight up, comes back down. What would a position versus time graph look like? What would a velocity versus time graph look like? What would an acceleration versus time graph look like? Well, it's moving in the plus direction, right? These are all considered positive. Velocity is positive originally, right? And the positions are all positive because this would be the 0 meter mark right down here. So we know it starts at the 0 meter mark, and we're definitely drawing a graph into the first quadrant. But since, let's think about the velocity first, if that helps sometimes. If the velocity starts off at some initial velocity, v initial, we know that as it rises up higher and higher and higher, it's actually going to slow down. So that means the graph is going to be going down like this, right? Then when we're right here, this is a velocity of 0 meters per second, right? This x-intercept. That's when it's at the top, v equals 0 at the top. And then it reverses direction, starts coming down. That's a negative velocity. That's these ones down here. These are all negative values in the fourth quadrant, right? And then if it struck the ground, then you'd have a stopping point for the graph. That, right? So thinking of a position versus time graph, it can't be linear, obviously, right? Because it's not going at a constant speed. Linear position versus time graphs only go for constant speed motion. It's slowing down. So somebody might want to draw a curve that goes like this, but that can't be right because the slope of the position versus time graph is the velocity, right? And if the slope is actually increasing with time, like I've just drawn, that would tell us that as it goes up, the speed is increasing. And that's not true. Speed is decreasing as something goes up into the air, right? Because the kinetic energy is transforming into potential energy, right? So I would have to have a curve, yes, but not the one I've drawn. It would have to be the reciprocal or the inverse of that. It would have to be a curve that goes like this, and that works because now the slopes are all getting less and less as you ride those up that curve. The tangent slope, the tangent lines at a particular point, these slopes that I'm drawing become less and less, right? And then right at the top, there's 0 slope. That's when it's up here, no speed. This is at top, which may not surprise you that in order for us to complete the graph, it has to come back down. So a position versus time graph actually looks like I've drawn an upside down parabola vertically shifted up and to the right. Right? And the acceleration, the velocity versus time graph has a slope, by the way, of 9.8 negative, which is why it's negative slope, because that's g, right? The formula that models this would still be v final equals v initial plus at, but v initial is whatever this v initial is, but really it'll be minus gt because the acceleration is really negative g, right? Negative 9.8. And then what would the acceleration time versus graph look like for something that's in free fall? Going up is still in free fall. Anything that's moving through space only due to with the only force acting on it being its weight is considered free fall. Anyways, the acceleration would be negative. It would be down here, right? You'd be coloring it in down here. And this dash, this mark would be the negative 9.8 meters per second squared mark, right? How about if we go over to this other challenging problem, which is something that has wheels on it like this, and it's pushed up with an initial velocity up the ramp, and they describe that it goes up the ramp, stops, and then returns back down the ramp. And they could ask the same question. What does the position versus time graph look like? What does the velocity versus time graph look like? What does the acceleration versus time graph look like? Usually, again, conventionally, we take the up the ramp as positive and down the ramp as negative. Just up in general is plus, so even it's up a ramp, it's plus. Down in general is negative, so even it's down a ramp, negative usually. But sometimes we teachers and textbooks say whatever direction it's moving in, let's just call that plus. But if we stick with that convention, up is plus, down is minus, right? So we would know that, same idea. As this thing goes up the ramp, motion map-wise, this thing would be slowing, right? Little smaller and smaller distances each interval of time, just like the ball that's going up in the air. It's the same idea. Then it stops at the top where it has no velocity at the top, and then it reverses direction and comes back down. And that motion map just stays there on the screen. It's just going in the other direction. The distances get bigger and bigger. Just like over here for the ball, as it returns down, the distances it travels each interval of time get bigger and bigger, right? So technically, what does the graph look like? The same. This would be colored down here. This would be your value for the acceleration. This would be the velocity versus time graph. Again, the x-intercept is at the top when it stops, right up here. Yeah. But this wouldn't be negative 9.8. This would be g sine theta, right? Because the acceleration down a ramp is g sine theta, assuming that there's no friction. It's just a fraction of g. Because sine theta is always a number between 0 and 1, right? And so it's a decimal. Depends on the angle. When you do it out, sine 45 or sine or whatever, sine 60 degrees, 0.63 or 0.52, 52%, 0.63, 62%, whatever. It's certainly not g. Right? That's only when all of your weight is pulling you in the direction of motion, like when you're in free fall. Then your acceleration is g. Acceleration is not your full g when you're on a ramp because it's a fraction of g. Why? Because only a fraction of your weight is pulling you down the ramp. Reminding you that the force pulling you down the ramp is actually mg sine theta, a fraction of your weight. Sine theta is fraction in all cases. Sorry, I'm just trying to redraw that. It's kind of messy. The force of gravity pulling you down is mg sine theta, right? So since the force, the net force, because remember the normal force and the other, the normal force that goes this way for the ramp scenario, and the y component gravity force, those are never of interest. Those cancel. The only unbalanced force is this one. That is the net force, percentage of your weight. And so F net equals ma, right? If the net force is your weight component, mg sine theta, on the ramp, like I've described here, then the acceleration down the ramp is a fraction of g, because the overall amount of force, F net, was a fraction of mg, fraction of your weight. It's also beautiful. Pause and admire it. The physics is just beautiful stuff. The math, the way the math describes the physical world is a beautiful thing to me. This is just introductory level. If you really love it, boy, it gets a lot better. You should keep going. So I just wanted to comment on those two things, because I'm really starting the Newton's laws of motion now, but those are still kinematics that probably I should have commented on. Those, again, a lot of concept questions in the multiple choice, a lot of graphs and things like that do surely turn up. And they're hard. Some of them are easier, but some of them are hard. All right. Usually I have my little, there it is. All right, so Dynamics, right? That's a fancy word that we use, dynamics. Describe Newton's laws of motion, dynamics. So where do I start? I mean, I guess Newton's laws of motion, I'm not going to write them all down, but I will remind you that Newton's first law is the law of inertia. An object in motion stays in motion as long as the forces on it are either balanced, or as long as the forces on it are balanced, or if there's no, I was going to say, or if there's no forces on it, like coasting through outer space. There's far away from any planet. There's literally no gravity and just no force, no forces. In those cases, then your acceleration, of course, would be zero if you're moving at a constant speed, and that is the law of inertia. That you would just continue moving at a constant speed in a constant direction. Direction wouldn't change. Every object stays in motion. In motion stays in motion. Every object at rest stays at rest. That's the law of inertia. Second law is F net equals ma, right? Which we can go back to. Sure, we're going to be using that a lot in the review, but that's the law that describes how something's acceleration rate, or the rate of change of speed, known as acceleration, including the direction, depends on the amount of unbalanced forces called the net force. It also depends on the inertia, the mass, right? That's essentially the ideas behind Newton's second law. Newton's third law, action and reaction. Every action causes an equal and opposite reaction. Every time you push on something, it pulls back on you in the other direction with an equal amount of force, not more, not less, always the same amount of force, but in the opposite direction. Those are Newton's three laws. Certainly I can write them down. What are some, common problems? Well, a lot of times we see the box being pulled, at an angle. They say that there's a force F. You might remember that. And they show this little dotted line, and they show theta. Sure, force is a vector. You're going to have to, resolve it into its components, right? In general, if this was our magnitude of F vector, then this is Fx, right? This is the y component. This is the angle that you're applying that force at, measured to the horizontal. What will Fy be? Magnitude of F sine theta, because that's how it goes. It's magnitude of the vector times the sine theta for the y component, as long as the angle goes from the vector down to a horizontal line. This is, in fact, going from the vector measured down to a horizontal line. Then y, again, goes with sine. And the x component would be magnitude of F cos theta. As long as that's true about the angle that I just said, then the x component goes with cosine, right? So you have, scenarios where, of course, they might say, what? No friction. Let's just say, nice and smooth. So let's just say there's no friction. What is the acceleration? Or let's even just do some, free body diagrams. We would end up having the normal force straight up. We'd have the force applied would be going, let's just say, up like this. And then the weight would have to be much more. It would be like down like this. Because remember that this upward lifting force, Fy, added to Fn gives us the total upward force. And that total upward force would be when you stick this one on top of this one. That gives you a total upward force like this. That would have to be balanced with the total downward force, which is the weight, G, right? You wouldn't draw it the way I just drew it. I mean, you wouldn't draw this in. Draw like that. I mean, and they're probably not even going to expect you to draw those lengths like that. They'd be happy if you just drew the normal force up, the gravity force down, the angled force to right. Free body diagram. You get all the points. You don't want to draw components. They don't want components in the free body diagrams, just the vectors. So if we were using Newton's second law, and let me also point out, some concept questions. If the person lets go of the box and just sitting there, then what happens to the normal force? If this force goes away because he just let go of it and it's now just sitting there, then what happens to the normal force based on my picture? It has to shoot up. Phew. It has to increase because now alone, the ground has to compensate for the downward force of gravity and push up harder to prevent it from falling, because boxes don't fall when they're on the floor. We know that's how things work. Right? So, but the moment he starts to lift at an angle or provide any lifting force, right? Even if a person comes over and lifts straight up on it with an amount equal to this is, let's say, some lifting force, then the normal force from the ground, the force from the ground will decrease by that same amount. right? So that they add up in the upward direction still to mg down. It's still, because this is a no acceleration, right? Balanced forces. Even in the case, again, where they do ask these questions, where somebody comes and applies a force that's in this direction. What happens to the normal force? A box is sitting on the floor, has some normal force, has some weight. Person comes and applies a force at an angle. What happens to the normal force after they start applying this angled force? The normal force increases. The normal force decreases. The normal force stays the same. We don't know without knowing the weight of the box. Oh, maybe. For all those 4 questions. Soon as there's an upward force, again, that's relieving some of the job of the ground, because now there are 2 teams lifting up trying to fight against gravity. Right? So as soon as there's an upward lifting force, in any way, shape, or form, the normal force decreases. The opposite would be true, of course, if somebody was pushing down at an angle on something. Something sitting here like this on the floor, and somebody decides to push down, and that's another problem, the downward angled problem. Right? This is now a downward Fy. This person is adding downward force into the box, pressing it harder into the ground. So previously, if gravity's force was like this and the normal force looked like this, nobody's touching it, it's sitting on the ground. I could just draw it all the way on the right of the page. Then somebody comes in and does this angled force down. What will happen to the normal force? Let's say it looked like this again, Fg down here. So this is what it originally looks like, a box just sitting on the floor. Then someone applies a downward force like I'm showing here. What happens to the normal force? The normal force pushing down harder on it, right? You push down harder and smush something into the ground, push really hard down on it, then the ground has to push up harder to fight against you, because the box isn't going to fall through the ground, because that's not what happens in our world. As soon as this downward force here is applied, the normal force shoots up, it increases. The gravity force wouldn't. And I haven't really drawn these correct. So I ran out of space. To draw it correctly, this gravity force, I guess, the way I've drawn it, would have to be really long so that, oh, wait, sorry. I think I did say it right. Apologies. So what we're looking at is that the total upward force now only comes, the total upward force only comes from the normal force. And that means that the 2 downward forces, which is this one plus this one, total have to equal this one up. So I didn't draw it perfect, but this in length plus this in length would have to equal to this in length, right? The bottom line, pushing down on something in any way, shape, or form increases the normal force, right? What about changing the angle? Sure, they're going to mention those things. Multiple choice questions. Box is on the floor. Man is pulling it up like this at an angle. And now he decides to increase the angle up to a new angle like this. F2, they call it. This is F1. What happens to the normal force as he is pulling the sled but decides to increase the angle of his applied force? What happens to the normal force? Well, if the original upward force was this amount and the new upward force is now this amount, right? Then by going at a steeper angle, you're applying more lifting force. Well, that will relieve the lifting force from the normal force, because the normal force is always pushing up. So if you decide to do something that provides more upward force, then you're taking that off of the job of the normal force. The normal force, which is the pressure under here, of course, would decrease. By how much? By however much you put up. If you put an extra amount of, well, that's not really properly drawn. Take that back. By doing what I've described here, if the first upward force was like this one here, and then the second upward force was like this one, once you go up to this angle, then this extra force in here, delta F, that extra upward force that you apply, the normal force would go down by that amount. Or vice versa. If they lower the angle, right, then your upward force here that you're applying by lowering the angle, now if we're lowering the angle, lowering the angle, then the upward force that you're applying to the box is getting smaller and smaller as you keep lowering the angle. And the normal force is, I have to make up for that. I'm going to have to start pushing harder up, right? The normal force would increase. Because in all cases, even if the box is moving to the right, that doesn't matter, right? The upward force has to equal the downward force for a box that's sitting there, and for a box that's moving to the right, and for a box that's moving to the left, both at constant speeds. Or if the box is moving to the right at an accelerated rate or to the left at an accelerated rate, it doesn't matter because it's not moving up, it's not moving down. So that means the net vertical forces still have to add up to 0. In which case, again, for the thing that's moving sideways, the 2 upward forces, or 3, or however many there might be, in total must add up to the total downward forces, which sometimes it's just gravity, or if someone pushing down at an angle, then the downward forces is gravity and the downward component of that downward angled force. Those are all ideas that are important. So what would the formulas be? Well, for just forces in general, as long as the angle is the way we usually write them, measured to the horizontal, then yeah, those are the way we would represent forces. How do we add forces? Vector addition. If this was F1 and this is F2, how do we represent F1 plus F2? We move F2 over to the head to tail. This is the head of vector 1. This is the tail of vector 2. And it's called the head to tail method because we literally touch the head to the tail. And then the resultant is here. This is the resultant, otherwise known as the net force. The net force is the resultant, the total force that's a result of these 2 forces acting simultaneously on an object. Something's pushing it this way, and at the same time, something's pushing it this way with those relative magnitudes. What direction will the net force be in? In the direction of the resultant. What will the magnitude of the net force be? The length of this resultant. Just reminding you how we add vectors. How do we subtract vectors? We have to flip them. How do we flip vectors? How do we subtract them? This one is F1. This one is F2. How would we do F1 minus F2? Yeah, you can put your little vector symbol over it. Who cares? Well, we start with F1 plus F2. At least that's how I like to think of it. Here's our F1. Here's our F2. Here's F1 plus F2. Then for us to do F1 minus F2, we have to flip F2. A negative vector is the opposite direction of the positive of that vector. So if this represents positive F2 in this direction, then this way represents negative F2. Right here, going this way. This is negative F2. It's really messy, sorry. Try my best. Negative F2. And then if we were to say, well, if this was now F1, this is negative F2, what does F1 minus F2 look like? Starts at the bottom of the tail of the first vector, all the way to the head of the next vector. There it is. This is now F1 minus F2. Yeah, you could put vector symbols over it if you want. This is the resultant of F1 minus F2. This is the resultant of F1 plus F2. Vectors add and subtract. And forces are certainly vectors. That's just how the world was created for us. By who? That's a different conversation. So now what are we going to talk about? What if we were referencing the acceleration? Common question. What is the acceleration of this picture? No friction. Well, we would always start with F net equals ma, right? And if we're talking horizontal motion, then we put an x there because the box is just going to move sideways, not going to fly up into the air, sink into the ground. So we have A is F net, the net horizontal forces divided by its inertia. And remember that these cancel, right? This plus this all add to 0. So the only unbound, right? Because this one added to this one just gives us that amount, and that's the same as that amount, as mg. They cancel. What's the only unbalanced amount? Right there, I'm coloring it in. This is the guy that causes the motion. He's unbalanced. That's Fx. Right here. Fx is F net. Right? Magnitude of F cos theta divided by the mass. This would be your model for, or way of computing it if they asked you to. The acceleration rate of this box pulled on a frictionless surface. What if there is friction? Well, let's start talking about friction to remind you about friction, and then we'll fold it back into this problem. These are not, super easy. These are questions. These are valid questions. These kind of questions. The angled box problem on a frictional surface for sure, 100%. So let's talk about friction, right? Friction, it's down here. So there's something moving along a frictionless surface. This is all rough. Here's our box. If we're pulling it, let's say, to the left with a certain force, and it actually moves in that direction, then that tells us there's got to be some amount of frictional force in the opposite direction. And the net force would be the difference between those two to the right. Right? We would say, this is vector addition, F minus FF at the tail. That's minus equals F net. That's the difference, right? It's the difference. You just come over to capital this F, and you just measure how long FF is, and you just take some scissors and you cut it away. Whatever's left is F net, right? That's the idea. That's the net force in this case, conceptually. But how do we work out what the frictional force is? You need to remember that the frictional force for kinetic friction, sliding friction, is the coefficient of kinetic friction times the normal force. If they're giving you situations where the thing is just being pulled sideways, which a lot of times they do, because at least that's a little bit easier. If it's an angled force, then the frictional force becomes more complicated to try to think about. Certainly can cover that. But FF, the frictional force, this is always true. The frictional force is always, for kinetic friction, mu k times the normal force. The static friction force, which is the force that exists under here as you're pushing it, but it hasn't quite moved yet. There hasn't yet become an unbalanced force. You're applying the force, right? Maybe this box is sitting here and you're applying just a little bit of force, 2 newtons, and there's a little bit of stickiness but underneath the box that fights back with 2 newtons. And in that moment, the box still hasn't moved. And you're like, but are you still pushing? Like, yeah, I'm still pushing. It just hasn't moved yet. Like right now, there's something on my table. I'm pushing it, pushing this giant circle. I'm pushing it. I promise you, I'm pushing it. It's not moving. That's however much forward force, backwards force is equal. What type of force are we talking about? That's static friction. Once I'm stronger than that frictional stickiness, the static friction force, it becomes unbalanced and then it moves forward. Static friction force has the same format. It's the coefficient of static friction times normal force. What normal force? This normal force. The same normal force we've always been familiar with. Again, if the applied force is just to the right, then that makes things a little easier for us because the normal force looks like this, and then the person comes and applies a rightward force like this, and what does the normal force now look like? It still looks like this, because this applied sideways force has no effect on the vertical normal force. The vertical normal force is still alone in its battle against gravity. It still has to equal mg down, right? Mg down, mg up. If it's sitting still, Fn equals mg. Yes. If it's moving to the right at a constant speed across the table, what is Fn? Mg. If it's accelerating as it slides along sideways along the road, getting faster and faster sideways, while it slides, what is the normal force? Mg. That doesn't change by anything that's forces that are sideways. Sideways forces don't affect vertical forces. And vertical forces don't affect horizontal forces. It's called the independence of motion if you want to read more about it, but that's the fancy topic, independence of motion. Sideways stuff doesn't affect vertical stuff. Vertical stuff doesn't affect sideways stuff. So these are on your equation sheet. Most of the time, we'd like to say if they're being nice to us and giving us this sideways force problem that I've drawn here, then again, the normal force is just mg. So in here, what do you stick for Fn? Mg. So what does this usually boil down to? The kinetic friction force is mu k times mg, right? This is the normal force. Or for the static friction force, mu s times mg. Is this always true? No, this is only true when the only forces other than gravity and the normal force Any other forces other than gravity and the normal force. Any other forces are just sideways forces. In this case, the frictional force sideways. Not going to affect our nice, neat formula like that we have here. This force over here is a sideways force. It's not going to affect this nice formulas we have. As soon as those change direction, FF never would. It's always sideways. But if this force all of a sudden became angled, now that's not correct. We can't use those nice formulas in the middle of the screen because the normal force isn't mg anymore. As soon as this force goes up to at an angle, there's an extra amount of upward force. The normal force is going to drop a little bit. We just talked about that, right? So this piece here would end up having to be mg minus f sine theta, if that were the case. Because if, again, this were now the force at an angle, like I'm trying to show here, at an angle theta, then this lifting force is f sine theta. This lifting force, this component, is f sine theta. And therefore, the normal force gets to go down because you're helping it out. You're all trying to fight against gravity, right? So if somebody comes and provides a little extra upward component force, like we've talked about, in the amount of f sine theta, then the normal force drops by f sine theta. So what will the new normal force be? Not mg anymore, mg minus f sine theta, right? So be aware of that. You can't, a lot of students, not all, but a lot of students want to look at this box here and be like, that's always true. Let's just use that. Friction problem, just use that. Sometimes it is. In fact, I'd say a lot of times it is, because a lot of their problems are, in fact, just sideways forces. As soon as there's some other vertical force other than Fn and mg, you can't make that assumption anymore. It's just not true. So, in summary, if I can try, Fn equals mg. If we return back to our original problem that I had drawn up here, which was somebody's just pulling it straight to the right, to the force F, then the normal force is mg. And as we said, our frictional force, Fk, would be mu k mg. In which direction? To the left. I mean, do you have to put a vector symbol over it? No. And if you did, I mean, yeah, you could put a little negative sign in front of it. Who cares? You just know if it's moving to the right, it's going, then that force is to the left. If it's moving to the left, then that friction force is to the right. If it's going up the ramp, then the frictional force is down the ramp. If it's going down the ramp, then the frictional force is up the ramp. The frictional force is always in the opposite direction of your motion, and so too is air resistance. I don't know how much they'll talk about air resistance, maybe a small mention of it. It's always in the opposite direction. Rocket's going up, air resistance force is down. Ball is falling down, air resistance force is up. So if we returned to our problem, which was how would we, this problem, determine the acceleration now involving friction? We can't just say that the net force, in this case, I now have, again, sideways force, F. This would have to be, erase this. The net force that we're talking about here would have to be the applied force minus the friction force, assuming that it's sliding to the right. But the net force just depends on the unbalanced amount of force, right? All divided by m. And then you'd have to re-express mu k times mg, all divided by m. That's the acceleration of something that's being pulled perfectly sideways with some friction. It's the applied force forward, which is the greatest force. It must be if it's moving to the right, minus a little bit because there's a little bit of friction back. UKMG is a little bit. How would we model that now again if it was at an angle? I kind of talked about it, but let's just put it all together. Box is sitting here. Man is pulling it like this. Again, the amount of force up is F sine theta. because that's theta. So the normal force gets to be a little less, than, right? So that this plus this equals this, right? But the bottom line is that the normal force would not be mg anymore. It's only just mg when it's just sitting there. Or if somebody's just pushing it perfectly sideways. We're now talking about somebody that's not pushing it perfectly sideways. They're applying some force at an angle. So the normal force has to be less by how much? By f sine theta, by this amount. I mean, if that doesn't make sense to you, you can always just say, hey, I've got three forces here. I've got this one, Fn, plus I've got this one here, which is f sine theta. And those two upward forces in the upward direction add together because they're both upward, and they have to be equal to our person we're battling against, which is the downward force of gravity, right? And now if I solve for Fn by just moving this term over to the other side, what do I get? What I wrote down, Fn equals mg minus f sine theta. So all upward forces equal downward forces because it's not a plane and it's not sinking into the mud. It's going to move to the right. And you just set up that idea. Left side is all upward forces. Right side is all, left side is, yeah, I said that right. Left side is all upward forces. Right side of the formula is all downward forces. And those two teams must be in balance. And then you can work out Fn. It's the way I was originally explaining. It doesn't make sense. So how would we express the normal force? I'm sorry, I didn't mean to say that. How would we express the frictional force? UK times Fn. Fn is, again, is like how much pressure is underneath the box. And, well, how much friction there is depends on how much pressure is underneath there. That's the Fn, right? So UK times mg minus f sine theta. This f in the f sine theta is the applied force, F. So that means, what would we have to do over here for the acceleration expression we previously had? We'd have to make some room for that. Mu k, as we have here, no, that's a little weird, wonky looking mg. Mu k, see how I have that over here? Mu k, I really have to put this in parentheses, mg minus f sine theta. Because this piece that I've just entered is the extra piece that we had to make room for. Usually we wouldn't put that extra parentheses there. That would usually. That's usually how we'd write it. Mu, and that's divided by m. Fa minus mu k in parentheses mg minus f sine theta, all divided by m. Complicated a little bit, yeah, for sure. Yeah, but you might see it. All right, I think I'm moving on. Talk about some other things. I don't have a lot of time left. Let's talk about the inclined plane. One of our famous things that we have to do. Inclined plane. I don't know, maybe it's sitting on inclined plane attached to a rope. How much tension is in the rope? Well, how much force is pulling it down? Mg sine theta. Totally need to know that. Put it in your brain. Keep it for a little while, at least until Wednesday. The amount of force down an incline due to your weight, due to gravity, is mg sine theta, fraction of your weight. So how much force must there be up the incline if it's not moving, since that's what's happening, just sitting there on the ramp. There's a rope attached to it. How much must that be? Mg sine theta. Mg sine theta up the ramp, mg sine theta down the ramp. What's the total net force? 0. What is the normal force? I don't know. I just know that when we're talking about the y component of gravity, right? When we draw this box like this, we draw mg down, and then we draw this y component right here. This is mg cos theta. That's the amount of gravitational force that's actually pushing it straight down into the ramp, pressing it against the ramp, mg cos theta. Right? So that means the normal force, which has to be in the upward direction, Has to be how much? mg cos theta. Has to be equal to this amount of the gravity force, which is down. So Fn equals mg cos theta. They could ask that, certainly. What's normal force while it's on the ramp? What's the tension? mg sine theta. What if sliding down, the rope breaks, it's now sliding down the ramp. What is the net force? I don't know. Is it friction? That matters. Maybe it's not. Maybe it's just going down a frictionless ramp. What's the net force? mg sine theta. Because the Fn and this one, mg cos theta, is the FGY component. Those cancel. So what's the only unbalanced force? Not that and that. Those cancel. mg sine theta. The net force is mg sine theta. What acceleration does that produce? G sine theta. The net force, again, is mg sine theta. So the acceleration it produces on a frictionless ramp is g sine theta, fraction of g. Once there's friction, I know. They're going to do it. Mean, nasty people. No, they're not. Just kidding. Pushing you. You should be pushed. Best in the world. There's friction on here. There's friction on this. Yikes, right? Yikes. We can handle it. We know that Fn is mg cos theta. Just store it to your brain, at least until Wednesday. And we already knew from before, and that theta again is the ramp angle. And we knew from before that the kinetic friction force, which any frictional forces problems mentioned in AP physics is usually sliding friction, kinetic friction. Sometimes they mention static friction. It's rare. The kinetic friction force is mu k times Fn, which means I can take away Fn and just plug in this expression for Fn, mg cos theta, right? So the frictional force on a ramp formula is that. If it's sliding down the ramp, then that amount of friction is up the ramp. How would we work out the net force now? No, you stick with it. What is the net force? Well, we know there's an amount of force pulling it down the ramp due to gravity, which is mg sine theta. We don't care about Fn and Fy because those cancel out. Boom, boom. The only unbalanced force as it slides down the ramp depends on this value and this value, right? So when we write F net, it would have to be mg sine theta down the ramp, Fgx, minus the frictional force, the sliding friction force, divided by m. What amount of friction force? We'd have to plug it in. I just worked it out all right here. This is it. That's our frictional force. Mu k mg cos theta. That's just this whole line I've just drawn is just the net force. It's just the net force expression. Mg sine theta is the force down the ramp from gravity. Mu k mg cos theta is the force of friction up the ramp. The difference of those must be called the net force or unbalanced amount, and that's all that produces the acceleration that we're solving for, because that's what we're doing. We're solving for acceleration. All divided by the inertia or mass. Acceleration of a block down the ramp. Try one more, because I'm almost out of time. I've got my period 8 students coming in. How about the Atwood machine? Remember the system approach. System approach is nice, because now we're talking about system, 2 objects tied together. Usually it's a rope, sometimes a pulley, 2 or more things moving together because they're tied together in some way. Heavy, light. Pulleys, who knows? Connected to the ceiling. Nobody cares. Just a pulley sitting there. And this thing can go up and down. We already know that the heavier one's going to go down just because we probably knew that. We could guess that from 4th grade. And this one's going to go up. Heavy things go up. Well, heavy things go down, I'm going to say. The heavier one will go down, the lighter one will go up. The real question again is, what's the acceleration of the system? Something you have to be aware of. Again, the internal forces are not of interest because internal forces cannot cause the center of mass of that system to move at all. Internal forces cancel. The internal forces would be the tension. If the tension force is this right here on him, then that same amount of tension is this on him. And since, yeah, you'd think those are both up, don't they add together? No, not really. I know you'd want to think that, but they're actually, if you straighten that out, right, pulled them off and straighten it out, those are pointing towards each other. Those are in opposite directions. Those are going to cancel. The net force due to just the tension force is zero. It's like pushing on my side of my body and trying to push myself across the room. The amount of force on my side of my body, but my body pushes back on my arm that's trying to push it, and they're both equal in amount. Newton's third law, opposite direction, they add up to zero. This guy has more force, right? This is mg. This guy has little, I should say, gravity force, little mg. So you're always just looking at the ends of these systems. Those are the two forces that are battling each other. Again, you could straighten it out if that helps you mentally and think, well, almost that time. Just trying to finish. You just imagine taking this whole thing off the pulley and putting it flat. Now the gravity force, which originally is down for the big guy, is now pointing this way in an amount of mg. The amount of this guy, this is supposed to be the pulley, sorry. The amount of force pulling on this guy is little mg. So what is the net force? Well, mg minus mg, big mg minus little mg, right? On the system is mg minus mg. This is the net force on the system. Someone's pulling it to the right. Oh, that's gravity. It's really down. I've just straightened it out to try to think about it. And someone's pulling it to the left. Oh, that's gravity. Just straightened it out to think about it. But the difference in their weights, that's the difference of their weights. Mg minus mg, right? Big mg minus little mg. It's the difference of their weights. So when you do the system, acceleration of a system is equal to the net force on the system divided by the total mass of the system. What is the net force on the system? I just did it over here. Big mg minus little mg, all divided by, how would we represent the total mass of the system? M1 plus M2. They probably would ask you to simplify that, because you can technically factor out a g from both of these. The textbook, they would show it as g factored out, capital M minus little m, all divided by M1 plus M2. That is the acceleration of the Atwood machine. It will always be a value less than g. You can pick any two numbers. Say little m is, I don't know, 2 kilograms. Big capital M is 5 kilograms, let's just say. What would this come out as? Just to make sense of the fact that it can't be g. And it can't, the acceleration can't be g, and the acceleration can't be more than g. No, that's forbidden. Laws of physics. What would we get? Capital M would be 5, little m would be 2 over 5 plus 2. That's 3 over 7 times g, because that's why this g is sitting on here. It's 3/7 g. Is that less than g? Yep, it'll only be 3/7 g. That's how you do that. That's how you get the formula. That is the formula. That is how you would apply it to some numbers. I'm out of time because period 8 is about to come in. Not done. No, not done. Definitely not done. Newton's laws has more, but hopefully this is going to help those who are sticking it out and watching these. I'm confident that this will help those of you that are doing that. I applaud you for it. We're almost there, just not yet. All right, guys, I will see you soon.